Good evening. Today our topic for discussion is refraction, which you have learned in class 10. So it's not a new topic to you, and this happens to be the first topic in your chapter ray optics. Now, the phenomenon of refraction is happening only if a ray of light passes from one medium to another medium of different refractive index. So, if you have a medium separation called the interface between two media, let's say this is the rarer medium and this is the denser medium like water or glass, and let this be air. Now, if we have an oblique ray is a ray that makes an angle of incidence I with the normal to the surface, and this is what you call as the interface between the two media. So this oblique ray, which is the incident ray, when it touches the interface, it will undergo bending when it passes from one media to another media of different refractive index. So if it's passing from the rarer to the denser medium, instead of continuing in its original path, it will bend towards the normal, and this angle between the normal and the refracted ray is what you call as the angle of refraction. On the other hand, if this ray was passing from the denser to the rarer medium, instead of continuing its path in its original path, it should have bent away from the normal. So this bending of an oblique ray as it passes from one medium to another medium of different refractive index is what you call as refraction. Now, you know the two laws of refraction, which is, the first one is the incident ray, the refracted ray, and the normal at the point of incidence will all lie in the same plane. And the second one, as you know, is Snell's law of refraction. Snell's law of refraction simply states that the ratio of the angle of incidence to the ratio of the angle of refraction is equal to a constant, and that constant is the refractive index of the second medium with respect to the first. So sin r by sin r is a constant. It is a refractive index of the second medium, that is refractive index of the denser, whichever second medium to the first medium is the ratio of sin I by sin r. And if you increase the angle of incidence, this angle of refraction also increases, keeping this n to 1 should be a constant. So this refractive index is a constant which depends only on the pair of media. For example, suppose this was air, refractive index n1 is equal to 1. If it's a denser medium, let's say water, then n2 is equal to 1.33 and n2 by n1 would have been 1.33. Had it been glass, then this would have been, for glass, it would have been 1.5. So n2 by n1 would be 1.5. So that's why I said this refractive index n21 is a constant depending on the pair of media. Also, it depends on the color of light, that is the wavelength of light. Because as you know, if you take the white light, VIBGYOR, this red has maximum wavelength and this has minimum wavelength. So this has the minimum refractive index, whereas violet color has the maximum refractive index. So basically this refractive index also depends on the color of light, that is the wavelength of light. So it's a constant depending on the pair of media and also depending on the wavelength of light. Then some of the other things that we need to discuss under refraction is something you've already learned in class 10 as refraction through a glass slab. You need to know the ray diagram, which I think you already learned in class 10. However, we will just go through it quickly. A glass slab has two parallel phases, right? And this is the, let's say it's kept in air. So this is glass medium and back to air medium. So we have the oblique incident ray making an angle of incidence I with the normal, and because this ray is passing from rarer to denser medium, it must bend towards the normal, and so this angle will be the angle of refraction, and naturally this also will then be r because they are alternate angles. And as this ray passes from the denser to the rarer medium, it will bend away from the normal, and this angle is what you call as the angle of emergence. Now, if you extend this incident ray, you will see that the emergent ray and the incident ray are actually parallel to each other, except that it is laterally displaced and this D is what you call as the lateral displacement. Lateral displacement here. So you need to know that the angle of incidence and angle of emergence will be the same. Incident ray and the emergent ray are parallel to each other, but they have a lateral displacement D. Then another thing we need to discuss under refraction is the phenomenon in which you would have noticed that, see, if you have a, let's say, coin lying at the bottom of a, let's say, bowl of water, you will see that this coin is slightly raised. Or you would have noticed if you put a glass slab onto your writing, you will see that the writing appears to be raised. And this is what we're going to discuss here, what called the real depth and the apparent depth. So what we have here is, we have a tank of water or any other liquid medium. So this is where your coin is lying at the bottom of the tank. So we have the object here. So this distance from the surface of the denser medium, this is the air which is a rarer medium, this is a denser medium. So this distance from the top of the denser medium to the where your object is lying is actually called the real depth. The actual depth is the real depth. Now if you're looking at this coin from here, let's say your eyes are here, then one ray of light that goes normal does not undergo bending because it goes along the normal. If I take another ray which is incident at an angle of incidence I, then this ray which is passing from the denser to the rarer medium must bend away from the normal, right? So now when your eyes are looking at these two rays, the image is always formed where two refracted rays meet. Minimum of two refracted rays must meet. So if you look from here, these two refracted rays are never going to meet because they are diverging. So you extend it backwards like this to find where they would have met. So this is where you will see the image is, because this is where you extended it backward, and this is where the two refracted rays appear to have met, and that is where you will see the image. So you see the object is actually lying here, but you're going to see the image in a raised position, and this distance from the top here to where the image is what you call as the apparent depth. The apparent depth. We are going to find a relation between the real depth and apparent depth with reference to the refractive index. So this angle being I, you know this angle also has to be I because they are alternate angles. And this is the angle of refraction because it is the angle between the normal and the refracted ray. So this also has to be R because it is corresponding angle, these two. Okay. Now I'm going to call this as P and this as Q. Okay. So if I look from this big triangle here, OPQ, I may write sin I is equal to opposite side, that is PQ by the hypotenuse, that is OQ. And if I look at that small triangle IPQ here, I may write sin R as opposite side, that is PQ by the hypotenuse, that is IQ. So sin I by sin R, that is Snell's law, which is n to 1 is equal to PQ by OQ into IQ by PQ, which is IQ by OQ. Now for small angles, if you are talking about very small angles of I and R, then what happens is, if you are talking of very small angles I and R, these 2 points P and Q will be very close to each other, this small angles, so this will be very close to this. So you may approximate this IOP to be equal to OQ and IP to be equal to IQ if these 2 points are very close to each other. So that I may write n to 1, which we know is sin I by sin R, is equal to, instead of IQ, I may write, I said we are approximating what? We are approximating OQ to OP. So OQ approximated to OP and IQ equal to IP. So we may write this as IQ as IP by OQ as OP. Right. Now, in this chapter, we always refer to the refractive index of the denser medium with respect to rarer medium. All the formulas are in that format. The final formula is always written as refractive index of denser with respect to rarer. Now, if you look at this second medium, the ray of light is passing from this medium and going into this. So, this happens to be the first and this is the second. So, if I write N21, we are actually talking about rarer with respect to denser. So, my final formula should be written as N of denser with respect to rarer, which is OP by IP. OP we know is the real depth and IP we know is the apparent depth. So, this is the relation we have between the refractive index and the real depth and apparent depth. The refractive index of the denser with respect to rarer is equal to the real depth by the apparent depth. Okay. So, that's what we discuss now. And next we have another topic coming under refraction, the total internal reflection, which is widely used now. It has many applications. Okay, so total internal reflection is because of refraction here. Total internal reflection referred to as TIR, total internal reflection. So here we have, let's say we have a medium where we have the normal here, the incident ray making an angle of incidence. Oh wait, let me take it the other way around. This is water, or let's say the denser medium, and this is the rarer medium, and we have an incident ray passing from the denser to the rarer. So this is the first medium, it's going into the second medium, and so it bends away from the normal, right? So this is angle of refraction and this is angle of incidence. The ray of light is entering from here, so this is the first medium, it's going into this medium, so that's the second medium. And because it is passing from denser to rarer, it bends away from the normal. So we already know that sin I by sin R we know is a constant. So if I now increase I, R also has to increase. So what happens is, suppose I increase I, make it greater than this, then this ray of light, R has to increase, will bend so much that it will graze the surface between the two, between the denser medium and the rarer medium, right? And this R becomes equal to 90 degree. And that angle is what you call as the critical angle. The angle of incidence at which the refracted ray grazes the interface between the two media is called angle of refraction. We will also see that if you increase the angle of incidence greater than the critical angle, then this ray of light will reflect back into the same medium following the laws of reflection, angle I equal to angle R. So this phenomenon in which two conditions have to be satisfied. One, ray of light has to pass from denser to rarer, because if it's the other way around, it will only bend towards the normal. So the first condition is ray of light must pass from denser to rarer. The angle of incidence must be equal to or greater than the critical angle. Then the ray of light will bend into the, reflect back into the same medium, and this phenomenon is what you call as total internal reflection. Now, if I look at this figure here, the second figure that I drew, we may write Snell's law. So, this is the first medium, it's going in from here, and this is entering the second medium. So, we know N21 is equal to sin I by sin R. And if we are talking about I as a critical angle, then this will be sin IC, and then R will be sin 90, and sin 90 as you know is 1. So this is N21 is equal to sin IC. This 2 is the rarer medium. So we are talking about rarer with respect to denser. I told you the format is we always give the final formulas in terms of refractive index of denser with respect to rarer. So refractive index of denser with respect to rarer is 1 by sin IC. So where IC is called the critical angle. And you will see this critical angle therefore depends on the refractive index of the two media, which means it is a constant depending on what? We already know this depends on the pair of medias in which the light is traveling. It also, I told you, it depends on the color of light or the wavelength of light. So NBR, this is a constant that depends on two things, that is the pair of media and also the wavelength of light. There are a few applications we need to discuss on this phenomena TIR. The first one is what we discuss under totally reflecting prisms. So in this case we take a right angled isosceles prism. So we have a right angled isosceles prism. So this is the angle A, which is 90 degree. We have angle B isosceles, so this is 45 degree. This is C also will be 45 degree. Okay. So so this is a right angled isosceles prism, and I am allowing light to enter through one of the isosceles sides. This is the base of the prism. These are the isosceles sides. So if I have, let's say, a object PQ, and I allow one ray of light enter the prism like this. This ray will not undergo bending because you know it's falling along the normal to this BA, and any ray along the normal does not undergo bending. But when it touches this face of the prism BC, I'm drawing the normal here, right? If this is the normal, then this angle becomes the angle of incidence. Incident ray, normal, this is the angle of incidence, which also should be 45 degree because this you know is 90, this is 45, so remaining 45 here. If this is 45, you know this whole thing is 90, so this also has to be 45. Now suppose the prism is made of a material whose critical angle is, let's say for example, 42 degree. Imagine. Then we know that 45 is greater than 42, or the angle of incidence is greater than the critical angle of the material. So this ray cannot go out. It will have to undergo TIR so that this and this will be the same. Angle of incidence equal to angle of reflection. So this will be the image of Q dash. Same way if I take another ray from the base of that object, it is incident on this face. This also being 45 greater than the critical angle. This will also undergo TIR, and we will see this is P dash. So now this is the image P dash Q dash. So what you have seen is your object is like this. You have turned the object through 90 degree. So you can use this prism to turn the image through 90 degree using TIR, totally reflecting prisms, whose critical angle should be less than 45, so that your angle incidence is greater than the critical angle. You can use this prism to turn the image through 180 degrees also. That is, instead of allowing the light to enter through the isosceles, one of the isosceles sides, you allow the light to enter through the base of the prism. Through the base of the prism. Okay, so let this be angle A, the 90 degree. This is B and this is C. This is 45. This is also 45. Okay. Now we are allowing the light to enter through the base. So we have P and Q here. So one ray of light, no bending here, but when it reaches here, this angle, as you know, is 45 degree because I told you before, this is 90, so remaining 45, this is also 45. So because the critical angle IC is 42 degree, if you have taken 42 degree, material of the prism having critical angle 42 degree, then this angle of incidence is greater than the critical angle, so it cannot come out. It has to undergo TIR, so that this is also 45 TIR. Now here we have another normal. So once more it will undergo TIR such that this becomes Q dash. Same way we take another ray here from the base of that object. This also undergoes TIR, 2 TIR. Here also it undergoes TIR, and you will see that this will be P dash. So now we have Q dash here, P dash here. So we have inverted image. Your object was like this. You have inverted the image through 180 degree. Okay. This principle is actually applied in the reflectors that you see behind the red plastic reflectors that you would find behind your bicycle or cars, where if you have a parked car, you can be safe. The reflectors will light up when your headlight falls on it. It's actually not a source of light, it's just a plastic red thing, is just a totally reflecting prism where you have, see, headlight from your vehicle will fall on the reflector, undergo TIR, double TIR, and then it will come out back to you itself. So what you're seeing is, from the reflector, what you're seeing is your headlight falling on the reflector, undergoing TIR, and then you get that light back itself. So when this source of light is not there, the reflector will just be a normal, it won't light up. So when the headlight hits on this reflector, it will totally reflect the light, and that's what you see. Then we need to go into another application of total internal reflection, which is the fiber optics, optic fiber. As you must have noticed, optic internet connection is the latest entrant into the broadband race, and it can actually give you some really fast speed and solid reliability. This fiber optic internet connection, I have noticed it because till now I have been using the cable connection, and it used to take me hours to upload a video if I was doing it during the peak hours. But now I've shifted to optic fiber. Fiber optic internet connection gives me really high speed for uploading, because in fiber optic the upload and download speeds are the same. So I can actually upload a video in maybe, let's say, seconds or minutes. It's that fast. Basically because it works under this principle of TIR, fiber optics, and the cables are made of glass or plastic, which is not susceptible to electrical and heat damages. Whereas the cable connection, which uses this copper coaxial cables, it's metal, and therefore it is susceptible to heat and electrical damage, which slows down the signal. There is loss of intensity, and therefore there is a slowing down of the signal if you're using the cable internet. Now here, what I'm going to show you is a fiber, optic fiber. An optic fiber is made of a material like plastic or glass, specially made plastic or glass, where this is called the core, and it has got a covering which is called the cladding made of, this is high refractive index, but this is low refractive index. So what happens is, if you allow a signal, see, you can convert your electrical signals to optical signals and allow those light signals to enter the cable, the optic fiber. Now, if this angle is greater than the critical angle of this material, this ray of light is passing from a denser medium to a rarer medium. So, first condition is satisfied. This light is traveling from denser to rarer. If the angle is greater than the critical angle, then this ray cannot escape into the outer. It has to be reflected back. It undergoes TIR. So, like that, it will undergo TIR at all points, and you will see that none of the signal is escaping into the outside, and therefore there is no loss in intensity, and you can transmit your signals therefore at high speeds through long distances. This is why internet speeds are very high when it comes to fiber optics. So also it can therefore operate at larger bandwidth, which allows you to operate many devices like your tablet, your phone, your TV, your laptops, all at the same time. And there is no lagging, because you see there is no loss of intensity. There is hardly any loss of intensity, and you can transmit your signals through large distances without any lagging in the speed, because you see there is no loss to the outside. Also, because I told you these are made of plastic and glass, which is not at all susceptible to electrical and heat production, whereas if you're using your copper cable network, you have copper coaxial cables. Copper being metal will develop heat and electrical resistance, and therefore there will be lagging in the speed as you transmit your signals. And so that is why now you see optic fiber is a very good option. Also, it's healthier, because these signals are actually trapped within the cable. They're not allowed to escape outside. So you are trapping the signal within this thin fiber, hair-like fibers are optic fibers, and so it is a healthier version, because if it's a metal cable, there will be radiation which is coming out of the cable. And so optic fiber, even in medicine, you use these optic fiber cables to, if you want to do an endoscopy, you use this optic fiber as the medium of transmission of signals from inside your intestines and other body, inside your human body. Okay, so we've discussed all about refraction in our class today, the phenomenon of refraction, then the refraction of light through glass slab, then the relation between real depth, apparent depth, and refractive index, and also this phenomenon called total internal reflection. Thank you.